A new video generation model by ByteDance, Seedance 1.0, is the best video generation model in the world right now, better than VO3 and Sora. The only difference is that VO3 can generate sound, so might be better in that regard. But other than that, this is the best one. And I think that super intelligence will have to do a lot with video generation, video processing. So let's learn about it. Let's get new ideas. So I really like that they have this table of contents. So let's start with model design. We have variational autoencoder, diffusion transformer, and then these two are less important. So if you don't understand anything in this point, you can just always ask ChatGPT, because a lot of you will have different backgrounds. So you can just open this paper and follow me and ask any questions like to ChatGPT as well. So variational autoencoder is going to just take the image pixels or video pixels frames and condense it down to a smaller representation space. So it learns to remove all of the unnecessary information, maybe even unpredictable information like how many leaves on a tree, but it condenses it down to just representation that there is a tree, maybe it has green or yellow leaves, it's autumn maybe, and this predictable information, as opposed to how every leaf moves, which a pixel level video predicts, which is unpredictable, and there is no reason to train on that and to train model to know exactly how every leaf moves, because it's unpredictable. So autoencoder consists of an encoder and decoder. Encoder compresses the raw redundant pixel information, there is too much unnecessary information, into a compact latent representation. So only keeps core, predictable, important information that we need to learn. While the decoder reconstructs the original input from these latent features. So you just train the AI, you give image, you train it to reduce the image into less information, so maybe 2 times less numbers, 2 times less information, and then from that less information, train the image to reconstruct the original image. So that's how you train variational autoencoder. And the decoder will learn to convert the latent representation into the original image. Now, it will not learn exactly how every leaf moves in a video if you compress it, but I think it's possible to create autoencoder that could even predict that maybe it can learn some way, even with less information, to in a compressed way, to predict like leaf movements. So I'm not sure if the video will be exactly the same or not, like exactly every pixel is the same. I think it will not, but I think that's how we compress information and computation and make it easier to compute. So the quality of the reconstruction of the decoder establishes the upper bound for resolution and quality of the image or the video, whereas the distribution of latent representations significantly impacts the convergence behavior of subsequent diffusion transformers. So latent representation is very important for when generating a video of it needs to understand the physics, how things work in the real world. This is really important. It's very important to work in latent representation space as opposed to pixel space that is redundant. So if we are adding some additional reasoning architecture that's not shown in this paper, but we are trying to make AIs reason, we need to do it in representation space, not in pixel space or token space. Actually, for LLMs, for token space, I'm not sure. Some people are disagreeing, so I'm still thinking about that. But for video, definitely in latent space, reduced space, because we will unlock a lot more computation while preserving most of the data and removing just unnecessary, unpredictable data. So what they do is they have this timestamp, which is the number of the frame in a video. Then they have height, width, and 3 channels are red, green, blue. And the autoencoder is going to convert that to things, but it will be downscaled. So you see you have T prime and T. And T is the downscaled version, smaller vector of T prime. So you can calculate the ratio by dividing T prime, the original version, with T, the latent space scaled down version. They use these values. So for time 4, which means they compress 4 frames into a single token, vector embedding, whatever. And they scale down height and width by 16. And then they use 48 channels, which makes it a bit very long or deep. I guess that's the way it learns better. So C refers to a number of channels or features in the compressed latent representation generated by the variational autoencoder. It's like token embedding vector in LLMs. And then this is the compression ratio. So C over 3 times these ones, which will be 64x compression ratio in this case. So the amount memory and computation necessary for latent space is 64 times less than the raw pixel space. So because they have higher compression, higher downsampling, they remove this patchification operation that's explained in this paper. They remove it in this paper as well. So what is that? This paper is by MIT, Tsinghua, and NVIDIA. So basically, because they are using a diffusion transformer, even this latent space frame or image is further broken down into patches. So the latent space from the autoencoder is typically further broken down into smaller, fixed size spatial blocks called patches, so they just divide the frame. This is the patchification process. Each patch then becomes a token for the transformer. So this paper from MIT is trying to solve the problem of diffusion transformer using too much memory. You know, they have quadratic scaling. So how do you reduce memory? It's actually, this paper argues it's better to have higher compression ratio than to divide into patches. So here where we are calculating the compression, it's just better to compress it down even further and even more in the latent space. So they completely remove patches in the diffusion transformer, according to this paper that I explained. So the training of the variation autoencoder is explained here, but ChatGPT explains this part better. So first we have L1 reconstruction loss, measures the absolute difference between the input image and the reconstructed image. Encourages VAE to reconstruct images that are pixel-wise close to the original. They also have this loss that's measuring against some model or pre-trained network that human find very good-looking images. So it's for perceptual quality. So this loss is trying to make it look good for humans, the images. And then also adversarial training adds a discriminator to distinguish real versus reconstructed images or videos. So this forces the VAE to generate outputs that are indistinguishable from real data. KL divergence loss. So it's important when we train on images that autoencoder learns generally to generate any image, not just images in the training data. So it needs to be able to interpolate between different images, not just memorize like the raw pixel values. And so it can just generate these discrete images that it saw, but it needs to be able to mix up concepts, mix up images to create new images that don't exist. So this scale divergence loss will make sure that the probability distribution over generating different images is a normal distribution. So it's a smooth distribution for every image, not just these discrete images that it trained on, but all of the images. So this third loss, I want to add, human eyes are more sensitive to structural and textural differences than to exact pixel values. This loss helps the model learn to produce outputs that look more similar and natural to humans, even if pixel values aren't perfectly identical. So this loss works inside of the latent space, not in the pixel space. And to add to the fourth loss, adversarial training loss. So sharpness and realism. Variational autoencoders alone can sometimes produce blurry outputs. The adversarial component adds a strong signal to generating sharp, realistic details and textures that are often hard to capture with just reconstruction and KL losses. So after they have visual tokens encoded by the variational autoencoder and text tokens generated by text encoder, they employ the transformer as our diffusion backbone. I really recommend watching these two videos, Scalable Diffusion Models with Transformers, Diffusion Transformer Explained and Explanation and Implementation, and this one, Building a Video Generation Model with Diffusion Transformers. So it's very well explained how these are used. So ByteDance is going to create separate layers in Transformer for temporal processing between frames and spatial processing within one frame, within one image. So these are for attention mechanism between frames and within a frame. So the spatial layers are responsible for individual frames. So visual quality, aesthetics, and understanding the text prompt. So they are only spatial layers are connected to text prompts. It takes both visual tokens, which is noisy video data, that it needs to predict the noise or predict the clean version later, and textual tokens. You need to know a little bit how diffusion works, so it's going from noise to clean image or predicting the noise. But they are using transformer to predict the noise, not the diffusion model. It's called diffusion because it's still predicting this noise, but there is no diffusion architecture, diffusion model architecture. It's just the transformer with attention mechanism predicting the noise. It's using multimodal self-attention. This is the only point where text prompt directly influences the video generation. The model learns to associate parts of the text prompt, a woman in a red dress, with the visual content of each frame. In short, the spatial layers are where prompt following happens. They ensure that each frame accurately reflects the description in the prompt. Temporal layers function to process information across multiple frames. This layer is responsible for creating smooth, plausible, and coherent motion. Input: it takes only the visual tokens that have been processed by the preceding spatial layer. As figure 2 clearly shows, the text tokens bypass this layer entirely. So you can see here, text MLP, we have that in the spatial block, but we don't have any text block in the temporal block. We can return to that image later. Let's continue with this. It uses standard self-attention layer that only operates on the visual tokens. So the temporal layers are where the motion modeling happens. They are blind to the text prompt and focus only on making the video move correctly. The main benefit of decoupled design of the temporal and spatial layers is efficiency. This is the primary benefit mentioned. A single unified spatio-temporal attention mechanism, where every pixel in every frame attends to every other pixel in every other frame, is computationally massive and expensive. And even if we talk about latent vectors, not just the pixels, it's still massive and expensive. By decoupling the tasks, the model can perform more focused, less complex calculations at each step, making both training and inference significantly more efficient. And then layers become experts in their specific jobs. So spatial layers get very good at generating high fidelity images that match text descriptions, leveraging knowledge from text to image models. So this is using the loss that trains it to do this. And temporal layers get very good at modeling physics and motion without being confused by complex textual semantics. So they use this multimodal diffusion transformer architecture from Stable Diffusion 3. And in the spatial layers, they have separate weights for adaptive layer norm, query key value projection, and MLP for the two modalities in spatial layers. So they have separate weights for text and visual images in spatial layers. To prevent training instability, the query and key embeddings are normalized prior to the attention matrix calculation. They also train this to generate text to image, text to video, and image to video. They do this by just concatenating a clean image or clean frames or before the noisy version that needs to be denoised. So then it just learns to denoise based on this clean prior image or video. So here they don't mention video to video. So I guess then it's just image to video. I'm not sure. I don't think they are using video to video. They are using both rope and 3D rope. They are using 3D rope for visual tokens. You can learn more what these rotary positional embeddings are. You can watch some YouTube videos or ask ChatGPT. It is a bit complex. If you hear this for the first time, you will need some time to understand it. So first, the model needs to understand the position of each piece of visual information, a token, within the video. A video is a three-dimensional structure, so time, height, so vertical position frame, and width, horizontal position within a frame. So they are still dividing frames into patches. I said in the beginning that they are not using patchification process. So this is confusing me as well right now. But it looks like they are using patches. Maybe they are just using different process or something. We'll figure that out later. But now we know that they are using patches, dividing frames into patches. The paper states they use 3D rope encoding for visual tokens. This means that each visual token is given a positional information corresponding to its time, height, width coordinate in the video. So why rope? This is going to be a bit dense if you don't understand rope. So unlike traditional positional embeddings that are added to the tokens, rope modifies the attention mechanism itself. It works by rotating the query and key vectors based on their absolute position, which allows the model to learn a relative positional information more efficiently. So it's just rotating these vectors. And if they are further apart, they will be rotated more. So model will know that if big rotation means these two are very far apart. So when it's calculating query and key between these two tokens, maybe it will learn to not to put less importance onto relation between these two tokens because they are further apart. And ones that are closer, maybe more relation, more emphasis on they influence each other more. But there is a challenge. The challenge is that the model's input is not just video. It's concatenated sequence of visual tokens and text tokens, so we also have text tokens besides the video from the prompt. The model needs to understand the positions of both. That's why they are actually using this multimodal rope. So this is an extension from 3D rope. This will also encode text. So this is how it works. 3D rope for visuals, as described above, the visual tokens get their time, height, width, positional encoding. 1D rope for text. The paper states they add an extra 1D positional encoding for textual tokens. Text is a one-dimensional sequence of words. The 1D rope tells the model the order of the words in the prompt. Example, this is the first word, second word. So this is just the classic rope for text. So they use 3D rope for video and the classic rope for text that is described here as every other model. So this multimodal rope supports interleaved sequences of visual tokens and textual tokens. So you can give it visuals for shot 1, caption for shot 1, visuals for shot 2, text or caption for shot 2, etc. So the multimodal rope will just keep track of where everything is, give everything positions. So then model can learn that, okay, well, this caption comes after this video. Maybe this caption is more related to this video than this caption is related to this video because it's not after. This is one after this video. So they have this diffusion refiner. So first the base model generates 480p videos, and then this model, diffusion refiner, this will learn to upscale this to bigger videos, 720p or 1080p high resolution videos. So they have this refiner that will upscale videos. So in the training of the diffusion refiner, the model is initialized from the pre-trained base model. So when they are pre-training this base model, they just use it also for this diffusion refiner, and then they need to fine-tune it, the diffusion refiner, for its specific task. So they train this model by starting from the real high resolution video and then scaling it down to 480p, and then when they scale up that 480p back to the 1080p, it will get blurred and it will still be low resolution. So they add noise to that video and then just train diffusion refiner to remove the noise and to get this clean, crisp 1080p video. So to summarize, they take big video, scale down, then stretch, but the resolution is still lost. Add noise and then denoise to create the original video. Then we have this prompt engineering part, prompt engineering. So the main problem is that the way a user writes a prompt is very different from the data the video model was trained on. So you see, user might say a knight fighting a dragon to generate this video, but the model is trained on this kind of very detailed, very specific captions that contain a lot more information, like cinematic, epic, fantasy style, dynamic, low. So it's a lot more detailed than what user would write. Because of that, if you just feed this user prompt, it might generate low quality or generic video because it's missing all the rich details it's accustomed to seeing. The solution, a prompt engineering model. So this LLM will just take user's prompt and rewrite it as this long, big, detailed prompt for the image generation, video generation model. So in the paper, they start with Qwen 2.514b and then train it specifically for this translation task. And this model is very powerful, very good. I think this is completely sufficient for this task because this task is actually quite simple. They did this post-training in 2 steps. So supervised fine-tuning and reinforcement learning with direct preference optimization. So they created these user prompt dense caption pairs. This is manually done by humans. They just manually created a bunch of these high quality prompts. And they separate text to video and image to video tasks because text to video describes whole scene, while image to video prompt often just describe the desired motion. For example, make her smile and wave. So user will send image and say, make her smile and wave. But supervised fine-tuning can still hallucinate. If you say a red car, it can rewrite the prompt as blue car driving fast. So it can change the meaning completely. So here in reinforcement learning, they create pairs of correct and incorrect generations. So if you have user prompt, a cat sleeping on a sofa, you have good prompt that explains the cat sleeping on a sofa, and the bad prompt that explains that cat is chasing mouse in the field. So this is hallucination. So they train the model to create good prompts and not to create these bad prompts using direct policy optimization. It looks like I can zoom in this text, I didn't even know. Let's talk about data. Scale, diversity, and quality of the training data, all 3 are extremely important and all 3 must be properly done. So data actually could be the most important part, even more important than algorithm or the compute. So this section of the paper, it might be most important, and it describes how they transform raw ocean of unstructured video data into something that's ready for the model training. So first, you need diversity, or your model will have a narrow worldview and style. So they ethically and legally sourced, as they say, content from a wide variety of public and licensed repositories. They explicitly aim for diversity across many axes: clip duration, resolution, subjects, people, animals, objects, scenes, nature, city, actions, genres, documentary, animation, artistic styles, and camera movements. So, raw videos can be hours long, but the model can only train on short clips. So you would not randomly cut 12 seconds clips, because that could lead to nonsensical cuts in middle of an action. They use both pre-trained AI detectors to cut the entire scenes, to distinguish between scenes, so they don't cut in the middle of an action or scene. And they also use some rule-based detection, not AI-based detection. And maximum length is 12 seconds of the clip that they use in pre-training data. They also want to detect watermarks, channel logos, hard-coded subtitles, and other graphics and remove them from training data. So they use machine learning models or rules to do that. They crop the frame while trying to preserve as much of the core visual content as possible. They also remove clips with visual defects like blurriness, jittering, low aesthetic quality, poor composition, static content, etc. with visual quality model. And this is AI helping make better AI. So this is the self-recurring improvement. They also want to remove duplicate content or very similar content. So they have some internally developed AI model that's gonna cluster these videos based on their similarity. And if some videos are too similar, they are too close together, or a group of videos, only the best video will remain and others will be discarded. And they have some quality score to determine that based on their internal model that I'm guessing they are not releasing that. And then distribution rebalancing. Raw dataset will naturally be imbalanced. Far more videos of cats than of zebras. This can bias the model. So they will analyze data distribution across various categories, subjects, styles, actions. And then they will use fewer examples of the categories that there is a lot of them, and use more examples, increase the usage of the examples of categories that are underrepresented. So now for each video they need to generate captions, or they need to fix captions if it already exists but it's not good. So they use these dense captions that I was explaining, very detailed descriptions of the video, and they train their own model to generate these captions based on video for each of the videos. So they use train it to be bilingual, both Chinese and English. Then they have this efficient engineering infrastructure. Goal is to process petabytes of video data efficiently, scalably, and robustly. So they use different hardware for different things. Video decoding on CPUs, AI inference on GPUs. They use open source tools and their internal tools to manage these complex distributed computing jobs. So they have scalability and fault tolerance, automatic retries, asynchronous communication. So all of this scalable, all of these things you need when you are training on a lot of big cluster of GPUs, CPUs, etc. Let's check the model training. So it's a multi-stage pipeline. Pre-training establishes a broad foundational understanding of video, images, and text on a massive diverse dataset. Continued training, a focused phase to specifically strengthen the model's performance on image to video tasks. Supervised fine-tuning refines the model on a small, ultra-high quality, human-curated dataset to improve aesthetics and motion. And then reinforcement learning from human feedback. the final polishing stage where the model is directly optimized to generate videos that align with human preference using AI judges, reward models. Here, this is pre-training. On the top, it has some issues like 3 legs here. Then continued training. This is makes it a bit better. Supervised fine-tuning, I guess it's also a bit better. And then human preference. So this looks best for us because it's literally trained to look best for us. Same here. Pre-training, continued training, supervised fine-tuning, and then human preference at the bottom. So pre-training is done in stages. Stage 1, start with low resolution 256 pixel images, which is fast and teaches the model basic object and scene concepts. Stage 2, introduce low resolution, so just 12 frames per second videos to teach the model about motion. Stage 3, increase resolution. And stage 4, increase the frame rate to 24 FPS to learn smoother, more realistic motion. This is the classic curriculum training. This is a lot better than just having one stage. So continued training, the pre-training phase is dominated by text to video. So continued training is for image to video capability. So here they increase the ratio of images to video data. They of course have high quality data. So it's important that here the first frame is already given. So the captions are usually going to just describe the motion, omitting description of the scene. This forces the model to correctly implement the motion action part of the prompt. Then supervised fine-tuning is they just have a small amount of high quality gold standard dataset. So they want to teach it to create this high quality data. Model merging, this is a unique and powerful technique. Instead of training just one model, they train several specialist models, each fine-tuned on a specific subset of high-quality data, anime, realistic human motion, etc. Merge the weights of these specialist models into a single, final supervised fine-tuned model. This allows the final model to inherit the strengths of all the specialists. They use low learning rate and early stopping to prevent the model from simply memorizing, overfitting on this small, high-quality data set. And then reinforcement learning from human feedback. Goal is to directly optimize the model to produce outputs that humans find appealing and correct. This is the final and most sophisticated alignment stage. First, they have humans create a dataset for human preference. So they generate these videos using their supervised fine-tuned model, and then have humans say video A is better than video B because, so this creates a data set of human preference. So they generate same videos based on same prompt, but they're gonna be a bit different. Then they use this data to create 3 different AI judges. Foundational reward model scores text video alignment and structural correctness. Motion reward model scores the quality, smoothness, and plausibility of the motion. And aesthetic reward model scores the overall visual beauty and style. Here you can see a reward model giving reward to our base model. So foundational reward model, you see the reward is increasing because the base model is learning to create better videos based on this reward model, better motion and better aesthetics as well. They apply this RLHF framework not only to the base model but also to the diffusion refiner, the model that upscales the video to 1080p. So this model is also optimized for human preference. Let's talk about hardware and training optimizations they did so they can train more efficiently. Of course, they start with CUDA kernels, where they fuse multiple kernels, multiple operations into a single big kernel. So instead of data going back and forth between memory and computation within the GPU, they just send data once, do everything they need to do without going back and forth, and then the final result goes back. So they fuse like row player normalization, and you need to fuse as many as possible operations into a single operation, so there is no sending data back and forth. Analogy: instead of making 3 separate trips to the fridge for milk, eggs, and butter, you grab them all at once in one go. This drastically reduces memory traffic, which is often the main bottleneck. So after you write your model code, after you design your architecture, then you work on fusing operations into one big operations wherever you can. They also have this data parallelism, where they send different parts of data to different GPUs, but they also split a single video to multiple GPUs. For example, 3 seconds of a video processed on one GPU, next 3 seconds on another GPU, etc. Another issue is when you are going forward pass, you need to save all of the activations, intermediate results for the backward pass. And this consumes a lot of GPU memory, which is very precious. So there are some tricks where you can discard some of the parts of those. You don't need to save all of them. You can just recompute some of them when you are during the backward pass. So this is trading memory for compute, which is what we want to do in this situation. If we are bottlenecked by memory, not enough memory, but we have available compute, then we need to use some compute to trade it for memory. And then another problem is that some GPU gets a small video, another GPU gets a big video. So this GPU finishes first and needs to wait for this GPU. So that's a problem. They use this system to distribute compute roughly equally to all GPUs. So actually, after you finish training, you can make the inference 10x faster. So when you have a big slow model, you can distill that into a smaller model. For example, if it needs to do hundreds denoising steps, you can train another model to actually skip every second and predict every second denoising step. So now you just need 50 denoising steps. So you are training another model to predict intermediate steps of this big model. TSCD distillation teaches the student to accurately predict the result of multiple teacher steps in a single leap. This gets them a 4x speedup. So I'm guessing it's predicting every 4th step here, so it gets 4x speedup. They also use this adversarial training plus human preference. So they train another model to try to distinguish between student generated videos and teacher generated videos. And the student is trying to make videos as similar as possible to the teacher, so the discriminator doesn't recognize them. They also optimized variational autoencoder. So this is also a major bottleneck. So they found the slowest parts of it and removed some reduced number of channels. So they achieved 2x speedup without quality loss. And then they also create kernels for inference and also quantization. So after you've trained the model, you don't need so much precision in your weights. So if you have 16-bit weights or 32-bit weights, you can maybe use 4-bit weights, 8-bit 8s, which they use. But you can also use 4-bit 8s probably. But that's not in this paper. I've also heard of 1-bit weights or 1.5-bit weights and stuff like that, but that's not in this paper. They recognize that many weights in the model are close to 0 and contribute very little. This system, ADA-SPA, can identify and skip these useless calculations, saving time. And then they also use parallelism to parallelize on multiple GPUs or GPU and CPU. So those are the optimizations for training and inference. So that was it for this video. I think this paper is really good. I think the video is definitely the future of AI, both video and text. So I think in the future we will have interfaces where AI is not generating just text talking to us, but it's generating video images. So I think we need to find ways to generate these videos to make them coherent, to make them conditioned on the context. So this is really interesting, really good. And there are many things here you can apply to other models like JEPA or other models that are not necessarily just about video or just about this video pixel level generation. You see at the time of publishing this paper, and maybe even now, this video generation model ranks first on artificial intelligence video arena leaderboard. Thank you for watching. You can check my other videos on my channel. We are trying to figure out AI and machine learning and build some highly intelligent systems and figure out the future and learn to do it ourselves. So thank you for watching and see you next time.